So first off, who am I? I'm Gian Merlino. I'm a committer and a PMC member on the Druid project. And I'm also a committer on Apache Calcite, so these two projects we're talking about today. And I'm a co-founder at Imply, which is a company started a couple years ago around the Druid project to provide product support and services for Druid. So what I want to talk about today, first off, what is Druid? Second off, what is NoSQL? Third, what's Apache Calcite? And then how we bridge this gap from NoSQL to SQL. And then finally, do try this at home, how you can apply the stuff we're learning in this talk to your own projects. So first off, Druid. How many people here have heard of Druid? Cool. That's awesome. That's way more than last time I talked about Druid. How many people are using it in production? OK. Next time, I want that to be a lot higher. All right, so Druid. It's an open source, high performance, column-oriented distributed data store. It's a mouthful, but let's talk about what that means. So we can pick apart the tagline. The first bit, high performance. To me, that means we want low query latency and we want high ingest rate. So we strive to be the best in those two areas. The second, column-oriented. So column orientation is a technique used by a lot of analytic databases, and it's what gets you highest scan rates on modern hardware. We're distributed, so Druid's deployed in clusters, typically tens to hundreds of nodes. The biggest clusters out there I'm aware of are in the order of thousands of nodes. We're also a data store, so the Druid cluster stores a copy of your data. It doesn't query it from somewhere else. It actually loads data into itself and queries it from within itself. That's actually part of how we get the high performance in the first bullet. So why does Druid exist? So Druid exists to solve a problem, which is good. We didn't just make it for fun. It takes a lot of time to make a database. The problem we were solving with Druid is OLAP slice and dice for big data. So OLAP cubes, OLAP systems were something that sort of fell out of favor with the big data era when the attitude became, let's just toss everything into a data lake and query it, and it's going to be awesome. We're all going to have a great time. It turns out we don't always have a great time because while that is a really flexible way to approach problems, it's not fast. And so we're bringing back that concept for the big data era. That's what we're trying to achieve with Druid. So what we're trying to do is power interactive exploration. We want you to be able to look under the hood of reports and dashboards. So not just have a dashboard, not just have a report, but also have everything on that report be interactive. So filtering on tiles, slicing and dicing, rotating through the data. We also want the data fresh. So we want to be able to do this interactive slice and dice analytics on real-time data. A really common use case for Druid is building an analytic application or powering an interactive real-time dashboard. So here's some screenshots of the application that we make it Imply. It's also called Imply. And it sort of demonstrates for you what kinds of workflows I'm talking about. So it's meant to be a very fluid, interactive workflow that lets you fly through your data. And obviously, this kind of workflow only makes sense if the data store is able to do sub-second or small number of second queries. And so Druid is a data store that does that. There's a lot of challenges. There's a lot of challenges in solving this problem, and these challenges all had to be tackled as we build Druid. So the first one is scale. Big data is tough to process quickly. You can throw it all in your data lake, and it'll work, which is a big step up from throwing it all in a single MySQL instance, and it's not going to work. So it'll work, but it's not going to be fast. It's hard to process it quickly. There's also a lot of complexity. So one solution that people sometimes do to power interactive or to power real-time dashboards is to pre-compute them. So you can take, there's a relatively common technique is to have a real-time data stream, run something like Kafka streams on top of it to compute essentially a derived topic with information for each of the visualizations on your dashboard. So it'll be updating in real time, but it's not going to be interactive. If you want to create a new tile on your dashboard, if you want to do a filter on it, you're going to have to spin up a new stream application, new stream processor. That takes time. It'll only operate on new data, not old data. So we want to operate on historical data too. So it's complex, and we don't want to pre-compute. There's also high dimensionality is another challenge. So there's a lot of solutions out there that will work with a small number of dimensions. So let's say, by dimensions, I mean attributes you can filter and group on, tags, that kind of thing. A typical use case for Druid has tens to hundreds of dimensions you can filter and group on. Concurrency, also very important. The idea is that once you have an application that looks like this and allows you to fly through data like this, a lot of people are going to want to use it. A lot of people will use it, and they're going to put a lot of load in the system, and we have to handle that load. Also, freshness. That's another challenge. We want to load from streams. We don't just want to do batch loads. We want to load data in real time. So what's the motivation for all of this? The motivation is that sub-second responses are really important because they allow a dialogue with your data. They allow you to fly through it in that way I was showing earlier. You get to do rapid iteration on questions. As anyone who's looked through data knows, you know that you have a question about data, you get an answer to it. The answer only leads to more questions. You want to drill down until you find what you're actually looking for, until you find something that actually is interesting. You know, I see my revenue dropped. Okay, why did revenue drop? Let's break it down by country. I see it only dropped in one country. Okay, I want to see in that country breakdown by product. Okay, in that product breakdown by sales by store. So every question leads to more questions, and we want to answer them quickly. If each one takes 2 or 3 minutes to answer, that's not going to work for us. This removes barriers to understanding. So a lot of people use Druid today. The Druid project's been around for a few years. We enjoy a good, robust set of production users. These folks are all on our Druid Powered By page. There's a lot of other people using Druid that aren't on the Powered By page, but these are at least the ones that have publicly talked about it. So you see a lot of big names there, Netflix, Hulu, Airbnb, and so on. This is a quote from Yahoo, who uses Druid throughout the company, but also at their Flurry division. This is a quote from an InfoWorld article. The performance is great. Some of the tables we have in Druid have billions and billions of events, and we scan them in under a second. So this is the kind of performance I'm talking about, and the kind of thing that lets you have a nice interactive data exploration experience on big data. So at least what I see as the key features of Druid are the following. There's low latency ingestion from Kafka. So we have very tight integration with Kafka, and we can ingest from Kafka in real time. You can bulk load from Hadoop as well. So we're integrated with both Kafka and Hadoop. So it really fits into the big data ecosystem. Druid can pre-aggregate data during ingestion. That's how we bring the OLAP concept into the modern age. OLAP was all about building cubes of summaries of your data. Druid can build those summaries on big data during ingestion. You don't have to do it. Druid actually can load your raw data, but it can also build these summaries. Druid is schema light. So when you have tens to hundreds of dimensions, one issue you have is, what if I want to add a new dimension? You know, in a traditional SQL database, we're talking about NoSQL here. In a traditional SQL database, you have to alter the table. You may have to update your indexes. A lot of times, this is an operation that goes offline, takes forever. In Druid, the schema is light. You can add a column anytime, remove a column anytime. It only affects new rows. So if you have new rows coming in with new columns, then they'll have those columns. Old rows won't have those columns. And you don't have to have a single schema for the entire Druid table. So the schema light ability allows easy schema evolution, easy adding of new columns. I say it's schema light rather than schema less, because if you're doing this summarization feature, pre-aggregating data on ingestion, you do need to provide Druid a little bit of information about your schema to know what to roll up on and what to aggregate. Yep. That's a good question, but ask me again after the talk, please. Right, so schema light. Ad hoc queries. Also very important. So I'm saying is with the Druid, you don't have to pre-compute. You don't have to deal with complexity that way. We deal with complexity by actually running every query on the data. We support both exact and approximate algorithms. The approximate algorithms are super important for achieving that performance I was talking about. So we support approximate counting, approximate ranking, approximate quantiles, and a few other approximations. A lot of times, it's not possible to get exact answers sub-second, even with a system as powerful as Druid. So we use approximations for those kinds of features. We do support exact responses. So you may find something like, I can do an approximate count in less than a second, and an exact count might take me 20 seconds. I do that offline. You can also keep a lot of history in Druid. Years of history are OK. So it's not what I would call a purely real-time system. It's a system that supports real-time data loads, but it also supports storing a lot of historical data in the same system. So if I had to sum up Druid in one sentence, it would be that Druid makes interactive data exploration fast and flexible and powers analytic applications. That's what most people using Druid are using it for, powering these analytic interactive applications. So that's enough about Druid. Now I want to talk about NoSQL. What is NoSQL? We created Druid at what I would call the height of the NoSQL movement. It was about 2011. MongoDB was really starting to take off. Cassandra was really starting to take off. At the time, a lot of people were using Cassandra for analytics, and we created Druid partly in response to that because we didn't think it made a lot of sense. We thought a system like Druid made more sense than a system like Cassandra for this kind of workload. But what is NoSQL? When researching for this talk, I don't even know what NoSQL is. Luckily, the experts don't know either. I did what I do when I don't know something that I want to get some research on. I go check the internet. The first link I found was Martin Fowler's website. He says there's no strong definition of the concept, which, okay, I don't feel so bad. I totally agree with that. But there are some early examples, and we can think about what NoSQL is by example. So early examples, Voldemort out of LinkedIn, Cassandra, still big, Dynamite, I haven't heard about recently, HBase, still big, CouchDB, MongoDB, still big. What are these things? They're very different in terms of architecture. Some of them are document stores, some of them are key value stores, some are graph databases, some are time series databases. They don't really have very much similarity in architecture. They don't have similarity in query language. So they're not similar in very many ways. What ties them together? So going back to the Fowler article I was talking about, he identified a few things that tie these together. One is that, obviously, they don't use SQL. So they don't use the relational model or the SQL language. Another one is they all were open source, designed to run on large clusters, designed to meet the needs of 21st century web properties around having massive scale, real-time data, and also having no schema, so being able to add columns without having a lot of controls around that. So let's categorize Druid. Is Druid a NoSQL store? We've never really called it a NoSQL store, but is it a NoSQL store? Well, we don't really use the relational model in Druid. We use a model that's almost relational, but it's not quite relational, and I'll talk about that in a little bit. One of the big things is that we're schema light. That's a big difference. We also, in the beginning, early days of Druid, did not support the SQL language, so we meet that first point. The second one, open source. Yes, of course, Druid is open source. Designed to run on large clusters. Yep, we got that one. We run on clusters of hundreds to thousands of nodes. Based on the needs of 21st century web properties. We got that too. We operate at massive scale on real-time data. If that's not 21st century web, I don't know what is. And no schema. So I don't know. I'll give this one like a 0.5 because we're schema light, like I mentioned earlier. Very, very easy to add new columns, but you can define a partial schema, and the partial schema definition is useful. So the one that really jumps out is the first one. The other four things are useful. I mean, open source is great. You get to look at the source. You get to fix your own bugs. That's awesome. You get to contribute. Running on large clusters is good. Big scale is good. Ability to evolve the schema quickly is good. But is it really good to avoid the SQL language and relational model? Well, let's look at what the relational model is. The relational model is, well, as the name suggests, based around relations. SQL calls them tables, and those tables have columns. And SQL queries suggest relational operations on the data. So relational operations are things like scan, where we're scanning a table. Project, where we're taking some columns out of the table. And so if you select just a couple columns, that's a project. Filter, where you have a where clause in your SQL. You're filtering based on some predicate. Aggregate, we're doing some kind of group by. Union, you're taking two relations and putting them together, just side by side. Join, you're taking two relations and not putting them side by side, but you're joining them on some key or some predicate. So these are the building blocks of the relational model and of the SQL language. So in a traditional relational database, you'll have something that looks like this. Let's say you have a database storing sales, and you want to be able to do analytics on your sales. So if you went to college, you took a course in database design, and you heard about normal form, you dutifully design your database in normal form, it's going to look like this. You're going to have a sales table, the timestamp, product ID, user ID, revenue. Product ID is a key into a products table. User ID is a key into a users table, so all the different objects, a sales, an object, product, user, they're all in their own kinds of tables. And they're related by keys. I didn't have enough room on this slide to have a city table and a country table, but if I did, I would have had those too, because a real SQL normal form purist would have wanted that country and city to be in its own table. So Druid and the relational model. Druid doesn't have tables. It has something called data sources. We call them data sources just to be different. A lot of things in Druid are named differently from what they're called in SQL databases. And part of it is to draw attention to the fact that they're not exactly the same as the tables. So we call this sales. In Druid, you can only query one data source at a time. So if you want to do an aggregate of sales, you need to essentially pre-join everything together. So you have the timestamp, you have the product name, country, city, gender, age, revenue, all in the same table, all in the same data source. Now, if you wanted to start adding a new field, like for example, let's say this is e-commerce, you want to add a field for the browser that the user was using, the kind of device. You would add that new field. New records would have it. Old records wouldn't have it. So it's as simple as that. You don't have to alter a data source. There actually is no alter data source command in Druid. You just simply add new records with new fields, and then they appear for those records. We do support something kind of relational model-ish, and this is one of our hooks into saying, maybe Druid is a relational model. Maybe the relational model makes sense for Druid. We support something called lookups. So we don't support joins, but we support lookups, and a lookup is much simpler than a join. So in SQL, a join can be on any condition. They're very flexible. In Druid, a lookup is a simple key value lookup. So it's essentially a function where lookup of product ID 212 equals office chair. So it's a special case, but it's a very important special case because a lot of real-world use cases for joins are addressable with this Druid functionality. So thinking about Druid and the relational model, does it make sense for Druid? Data sources are like tables. Okay, there's some differences, but there's a lot of similarities. Druid lookups apply to a common join use case. So we actually even can we can think of Druid as having multiple tables you join together, even though Druid wouldn't call it that. It still looks like that to someone that wants to fit it into the relational model box. And despite what you may have learned in college, big flat tables are common in SQL databases anyway in the real world, because when analytical performance is critical, they tend to perform better. So even in a honest to goodness SQL database, you might still see someone doing this exact same schema design that you would do in Druid. And there's benefits to offering SQL. Developers and analysts know it. So Druid has a native query language that you have to learn, reading the documentation. SQL, you also have to learn, but the benefit is that there's textbooks written about it. No one's written a textbook about Druid yet. And also integration with third-party apps. So we built Druid SQL a couple of releases ago, and within about, half a year of releasing it, we started to see support from third-party companies like Looker supporting Druid. And that kind of thing is possible because their developers already knew SQL, and it's much easier to integrate some app that already speaks SQL with a SQL database. So there's benefits. Let's say, okay, the relational model makes sense for Druid. Druid's data model is not exactly 100% fit with the relational model, but it's close enough that it makes sense. And there's a lot of benefits to offering SQL as a query API for Druid. So how are we going to do it? That's where Apache Calcite comes in. Apache Calcite is a project that does everything about a database other than actually store your data. So you may think that storing the data is the important part of running a database, but there's a lot of other stuff involved too. So there's SQL parsing, query optimizing, a query interpreter, a JDBC server. So all this stuff other than the actual storage and computation on top of the data. It's very widely used. So Druid uses it now. It's also used in Apache Hive, Storm, Samza, Drill, Phoenix, and Flink, and a bunch of other projects too. From what I've seen, its adoption's really started to skyrocket in the past couple of years because it's a super useful way to add SQL support to something that didn't support SQL before. I think that I think that if you look at the whole NoSQL thing, My personal guess is that it actually does SQL does actually make sense as an interface to a lot of these tools. It's just hard to implement a SQL database. You have to do all this stuff. You have to parse SQL. You have to optimize it. You have to interpret it. You have to have a server that connects to existing drivers. It's not easy. It's easier just to make a native query language that corresponds directly to what the database does. But with Calcite, you don't have to worry about that stuff. So it's relatively easier to add SQL to something that didn't support it already. So what Calcite does internally, you take SQL, it parses SQL into a SQL node parse tree. The SQL node is a Java class. This is all Java, by the way. I didn't mention that, but Druid, Calcite, all these things, all Java. So it parses it into a SQL node parse tree, a Java class. That is if you're familiar with how parsers or compilers work, this is the first stage of compiling something is parsing into some sort of syntax tree. That's a SQL node tree. The second step is converting that into some kind of operator tree. So not just the tokens of the parsing, but actual operators of what logically we're going to do in the data. So we become a logical operator tree. And then the final step is optimizing those operators based on the target calling convention. And the calling convention is a Calcite concept that just means where we're getting the data from and what's going to process it. So Druid is a calling convention in Calcite. So here's a SQL query. How many of you all know SQL? OK, awesome. So this is a very simple SQL query. It's just a grouping by a field called dim1, also applying a filter on dim1, and selecting the number of rows that each of those values appears in the table. So we're going to get 3 rows out of this, or up to 3 rows, 1 for each of those things we're filtering on, and a count for each one. Calcite will parse it like this. So this is the parse tree that we're going to get. There's a keyword for select, identifiers for the columns, the tables, the schema. The count is an operator, where, group by, are keywords. And then the thing we're filtering on is literal. So it's going to parse it like this. Next, it's going to convert that parse tree into a operator tree. So for this, the operator is first a scan. So remember, a scan is we're just going to scanning data from the table. Second is we're filtering. So this is where we're applying that in filter, or 2 equals ABC, or DEF, or GHI. Then we're doing a project. So we're saying we're not interested in anything other than the second field, dim1. And then we're doing aggregation. So we're grouping by the first field out of the projection. So these are all relative to the one beneath them. So we're grouping on the first field, which is dim1. And then we're aggregating a count on top of that field. So this is how Calcite would represent the unoptimized or logical operator tree that has not yet been converted to Druid, or to whatever it's going to convert to. Obviously, Calcite doesn't just work with Druid. Then finally, there's the planner that's going to take that basic logical operator tree, and it's going to convert it into the calling convention of the target data system and optimize it. So the query planner in Calcite is a framework that you can plug into. And a lot of what Druid, the meat of the Druid SQL implementation in Druid is plugging into the Calcite query planner. So the way that the query planners work in Calcite, they have rules that match certain relational operator patterns. So for example, you might have a rule that matches a filter followed by a project and can swap them. So basic things like that. So reordering things. A lot of them do that. Some of them do stuff like simplifying expressions, reducing expressions, that kind of stuff. So these planner rules can transform one set of operators into another. And the new set must have the same behavior, but it may have a different cost. And so by applying these transformations, Calcite will try to find a set of operators that works in the target calling convention and that has the best cost. There's 2 kinds of planners Calcite does. One is called the HEP planner. It's heuristic. It just applies all rules that match in a deterministic order. That actually is not cost-based at all. It's just applying a set of rules you give it if they match. And the second one, Volcano Planner, a little bit fancier. It's cost-based, and so it'll explore all possibilities. It can't actually hit all of them because the search space is too big. It'll sort of go a little bit down. It'll go a little bit down a tree, and if it goes too far, it'll sort of, without getting a good cost, it'll give up. But it'll explore the optimization space and try to find a best cost-based plan. So how do we use Calcite? It can be used in a couple of ways. It can be embedded, or it can be used directly by end users through built-in adapters. So Druid SQL embeds Calcite. We depend on Calcite as a library, and then the Druid SQL API is offered to Druid users over a network socket. So Druid users don't use Calcite. It's internally used to Druid. You can use Calcite directly. It's actually, if you search online for this after the talk, you'll find it gets a little bit confusing because if you search for Calcite Druid adapter, you're going to get the second one. You'll get something that you can use directly. It actually won't use Druid SQL at all. It'll speak Druid's native language to Druid because Calcite can also be used in a mode where you run it directly, and then it makes queries out to other data systems. And you can use that kind of thing to say, you want to join some data in Druid with some data in MySQL. You actually can do that in that direct mode. It may not be the most efficient query plan because it may end up pulling 100 gigabytes of data out of Druid. And so it may not be the most efficient thing in the world, but logically that's what it's doing. Anyway, Druid SQL embeds Calcite. Users don't need to worry that Calcite's there unless they get an exception message that comes from it. Okay, how did we bridge this? How did we go from NoSQL to SQL? Obviously, we use Calcite, but let's look at Druid's native query language now. This is like a 6-point font, and I'm sorry about that, but one of the reasons that we added SQL, in addition to people already know it, is that Druid's native query language is really verbose, and I hate typing it. And probably implementing Druid SQL saves time in the long run because you don't have to type so many of these things. So let's look at the query on the right as a SQL query. Based on the hands earlier, a lot of you can probably read it. So this is basically doing a time filter on a few days. We're looking at a specific channel of Wikipedia, so the English subside of Wikipedia, and we're getting the amount of bytes that have been added, or amount of characters that have been added by country. So group by country, some bytes for English Wikipedia over about a week. We can map some of these things on the Druid queries. So, Druid queries Druid is essentially, it's a slice and dice system, which means the queries it's doing are all basically aggregation queries, or selects and aggregations. And so a SQL query that's doing selecting or aggregating can map onto a Druid query. So the from Wikipedia in the Druid query, that would be data source Wikipedia. Group by country name is the next part that appears. That's dimension country name. So this is a top-end query, which means we're doing a ranking. So we're ranking countries by the amount of bytes added. The next part, the where, expands into this two-part filter in Druid. So in Druid, everything is time indexed, and that's for Druid is a native time-aware database. It's not, I wouldn't call it a time series database, but it is time-aware and has a lot of optimizations around time in order to get data inserted and filtered quickly. And so because of that peaks out in the native API, and there's a separate section for time filters called intervals. The SQL, of course, there's no such thing. Time is not special, so the SQL adapter needs to split that out. And there's also a filter for all the other filters that aren't time filters in the native language. The sum added becomes this little JSON block over here for aggregations. The order by becomes this metric section, and the limit becomes a threshold. So that's how the SQL query maps onto a Druid query. A Druid query in general, the Druid execution pipeline internally looks like this. Druid queries always follow this pattern. They don't have to necessarily go all the way. Like it could just be a prefix of this, but it's going to start with a scan, then maybe have a filter. It's optional. Maybe do a projection, maybe do an aggregation, maybe do another filter after the aggregation, so that would be like a SQL halving, maybe do another projection after the aggregation, and then maybe do a sort finally. So the sort would be like an order by and limit. So every native Druid query looks like this. So when we do a SQL to native translation, remember back to what Calcite's going to represent this SQL query as, the sequence of operators. That sequence of operators, we map it onto a partial Druid query object. So if you open up the Druid source code, search for partial Druid query, you'll see that it's an object that's got 7 fields in it, and those for each one of these things. We map onto that in that order. One of the reasons it's so important that Calcite comes with built-in rules to swap orders of things like filters and projects is because Druid is very rigid about the order it does things in. And a SQL query may not, it could be, the operators could be in any order. And so what we do is the Calcite planner is responsible for reordering things into this order. So then finally, this partial Druid query can be converted to a Druid query using this toDruid query method on that object. And this is the Druid native query that comes from that partial Druid query. So how do we split the work up? Calcite does some, Druid does some. Calcite implements a SQL parser and a basic set of rules for reordering and combining operators. So Calcite's a thing that knows, I want to push a project into an aggregate. I want to swap a filter in a project. It knows how to do that. It also implements the framework for the rule-based optimizer. What Druid does is we build a Calcite catalog from Druid data sources. So the catalog is a list of tables, a list of columns in those tables. So Druid builds that up and gives it to Calcite. Druid implements cost functions for partial Druid query to guide the reordering and combining operators. So we implement all these get cost methods that Calcite uses. Druid has its own rules to push operators into partial Druid query. And Druid implements the functionality to convert those partial Druid queries into actual Druid queries that can get run. So this translation has, of course, there's some performance overhead. It does take time to go through all these steps. The performance overhead is relatively minimal. One reason for that is because the actual execution of the native query is unchanged. The only overhead there is the overhead of doing the planning, of turning the SQL query into a native query. So here's some benchmarks I did. You see the difference is usually in the 20 to 40 millisecond range between SQL and native based on the size of the data set. Looks like the overhead is not really a percentage overhead. It looks like it's a roughly constant, just a few tenths of milliseconds. This was an overhead done on localhost. One cool thing is that it actually, in real life, SQL can be faster than native because it transfers less data. The Druid native response is a little bit it's as verbose as the Druid native requests, and the SQL response is just an array of values. So when you have the network part of the mix, actually it can be faster overall. So there are some challenges too. I said that Druid is not an exact fit for the relational model. What are the challenges we faced? So we did build this, we shipped it. We have a lot of people using this functionality, but let's talk about the challenges we faced. Druid schema-light, again, we have flexible columns and flexible types, whereas SQL is more rigid. You have specific types for columns. So in the Druid native query language, we deal with the schema-light situation by we apply a schema on read. So on read time, the user says, I want to coerce types in a specific way. So the user specifies, I want to treat column XYZ as a string. In Druid SQL, we can't do that because there's no such thing as type hints in SQL. So in Druid SQL, what we do is we take the latest metadata. So if XYZ was changed from integer to string at some point, we'll call it a string because the latest data has string. Another challenge, think back to lookups. So we look up this product ID to name. If you're a SQL expert, SQL purist, you may want to write this as a join. You may want to join a sales table on a products table. In Druid, you can't do this because Druid doesn't support joins, and so Druid SQL doesn't have a join keyword. You can write instead lookup ID products as product name, and this is how you access Druid lookup functionality. So the functionality in the end is the same, but the way you write the query is a little bit different. Another challenge, writing good queries. SQL makes it really easy to write inefficient queries, as I'm sure anyone that's struggled with a query planner knows. Databases really try to optimize it as best as they can, but the explain tool is essential. In Druid SQL, the explain tool tells you the Druid native query that will run for a specific SQL query. If you're optimizing performance, it's super important to explain the SQL query, look at the native query, learn a little bit about how Druid's internals work, and then use that to optimize your SQL query. I think that the dream of databases is that users never have to do that, but I've never met one that lived up to that dream. Sorry, one sec. So some future work in Druid SQL. There's some Druid features that are not supported in Druid SQL as of the most recent version. So multi-value dimensions, spatial filters, theta sketches, not supported. Another one is join-related stuff. So we want it to be possible to write a lookup as a SQL join. It's, I said earlier that you write it as a function. It'd be nice to make it possible to write it as one, and then under the hood translate that. So basically improving the SQL to native translation mechanism to recognize that join, turn it into a lookup. Other stuff, SQL window functions, SQL unions, SQL grouping sets. These are features that are useful for analytical apps, and we don't support in Druid SQL right now. So finally, do try this at home. This is the Druid community site at druid.io. My company, Imply, also has a distribution of Druid that's basically Druid plus that UI you saw earlier and a few other goodies. That's imply.io/get-started. You can contribute. We're hosted on GitHub. We got a community page on our website, and it's github.com/druid-io, or just go to druid.io and click on community. Also, really recent and big news, Druid's recently begun migrating to the Apache incubator. So Apache Druid is coming soon. And that's my last slide. Thanks, everybody.
Okay. We have time for 2 short questions or 1 long one. First hand up. In the back over there. All right. I'll run really quickly.
Question on when you mentioned you can join with other databases, like a federated join, where does the data move to Druid or to the Calcite?
Yeah, so I mentioned that was possible when you're using Calcite directly. So again, Druid SQL embeds Calcite, so you're not going to be able to do that through Druid SQL. If you download Calcite, install it as its own thing, not using Druid, it can do stuff like that. And unfortunately, what's going to happen is it's going to pull data from Druid, pull data from another system, and do the join on your machine. It's probably not going to be practical.
Obviously, there's a way to delete data or have it like auto-purged over time, since it seems like it's continually ingesting? That's possible?
Yeah. So I mentioned that Druid's a time-aware database, and we use that time awareness to optimize things. One of the things that we do with time awareness is you can set a retention rule saying I want to drop any data older than a certain amount of time, so 30 days. Another thing you can do is you can just manually hit one of the Druid APIs and say I want to drop all data from this time to this time. So it's a time-based drop.
I think in one of your examples you had it compile a SQL to a top N. And that's an approximate exam. That's an approximation, correct? That's
yes.
Not a. Is there any way to hint it in the SQL to use a group by instead?
There is, yeah. So I didn't cover that here, but we do have hints like that. The hint in that situation is use approximate top N. So by default it's true, but you can set it to false, and then it won't do that. There's also a hint for use approximate count distinct.
Okay.
Also, there was the granularity was set to all. Is there ways to specify in the SQL to use different granularities?
So the way that works is if you have if you select floor of time today, so there's a time floor function. So if you select a time floor function and group by the same time floor function, the translator will turn that into a granularity.
Okay. Oh, question over here. All right.
Since you mentioned it's a Schema-light, I wonder, is it friendly to JSON data type ingestion?
Yeah, so the data types we support are CSV, TSV, JSON, Avro are the big ones. There's also an extension for protobuf. Obviously with TSV, you need to define everything up front because we don't know what your columns are. With CSV, we can pull them out of the header row if you have one, if it's a flat file. And if it's coming from a stream, it's going to have to be JSON or Avro. So
if JSON attributes document, change over time slightly, do you have, built-in function to consume the change into your Schema-light tables, data sources automatically?
Yes. So basically what happens is the way that the Schema-light stuff works is you tell Druid that you want to treat any fields that you didn't tell it about. So you can specify a partial schema, and you can say, I want to treat any fields I didn't tell you about as dimensions. And so, if it's doing its summarization, it'll treat them as a dimension. If you've got summarization roll-up turned off in just in time, it'll just treat them as like a string column, and it'll come into Druid automatically for any fields you didn't explicitly tell it about.
All right. Thank you all for coming. Please don't forget to fill out your speaker evaluations, and otherwise enjoy the festivities this evening. Thank you.
Thanks. Yep.